Right. So last time, which was probably long ago, what we had said was just extending the covariant derivative, we defined a covariant divergence of a vector, and we also defined the covariant divergence of a tensor. And yeah, and then so we said that, like, for example, Maxwell's equation, you have Fij divergence is current density. So in the four-dimensional, in the curved space-time, I mean, for current density. So in curved space-time, this covariant divergence has to be replaced by, the divergence has to be replaced by covariant divergence. So we have Fij semicolon j is equal to j power I. I mean, j power j, ith component of j, where I equal to 0 refers to density and I equal to 1, 2, and 3 refer to the current densities. All right.
Yes.
And for example, if suppose you take a Gij, in fact, this is actually the metric tensor for a black hole. So I mean, right now I'm just taking it as a given metric. Okay. Suppose I have this, then the coordinates are t, r, theta, and phi, and the ds square is written this way. Now, f semicolon j, Fij semicolon j, since Fij is an antisymmetric tensor, I had mentioned
Yes,
that
could you please zoom that in? Like, what is the subscript of R there?
What's it?
In the Gij
S,
matrix.
S, S.
Okay.
That is for, okay, that is for Schwarzschild radius. But I mean, I am not using the fact radius, but it's some parameter, constant. Okay. Hello?
Yes, yes, got it.
Okay. So Fij covariant divergence J can be written in this form. And here, if you take square root of minus G from the Gij given there is just R square sine theta, because these two will cancel. We'll just get a minus sign. You know, when you find the determinant, since the diagonal matrix, that's just the product of the diagonal components. So the 0th and the 0, 0 and 1, 1 component get multiplied and produce minus 1. And so this is just R square sine theta. And then G upper Ij is given by this, is the inverse of this. So if I substitute all this in that, I can write the modified equations. In the limit, when Rs is very small, then I expect that it should give me some kind of a Newtonian limit. So that is basically the thing. In fact, when Rs is exactly 0, then I will get the usual Minkowski flat space-time Fij. Okay, so this is how you use it. Is it all right?
Yeah.
Yeah, okay, fine. Now, we now come to an important issue, which is, how do we know whether a space-time is flat or not? When do you call a space-time as flat? So probably I'll just open up. Okay, I will do another thing then. I will just keep. Okay, wait. Okay. So I will use this and then I will open this, just a minute. Okay. Right. So now, when do we say how to probe if a space-time is flat or not? Now, if Gij is equal to eta ij, of course it is flat. Okay. But the converse is not true. Okay. That is, if Gij is not equal to eta ij, does not necessarily mean curved spacetime. For example, if I have ds square is equal to dt square minus dr square minus r square d theta square minus r square sin theta d phi square. Sin square theta, right? Sin square theta d phi square. Now here, clearly, Gij is not a constant. Okay? It is coordinate dependent. But is this flat space-time?
Yes.
Yes.
It is flat space-time because, but flat space-time because you can make it from spherical polar to flat, to Minkowski. Okay. So what it means is, if Gij can be made eta ij by a coordinate transformation, it implies that the space-time is flat. Although this is as a matter of principle, this is a good criterion. It is not practical to use. Not practical. Why? Operationally. Okay. Suppose I may be having, suppose 1,000,000 transformations are tried. Do not make Gij to eta ij. But 1,000,000 plus 1 transformation might. In other words, if I am able to find a transformation which makes it eta ij, I know that it is flat. But just because I am not able to do it by finite number of transformations does not mean it is curved, because there are infinite number of transformations possible. So this is not a practical method to find out whether a space-time is flat or not. Okay?
Yes.
Okay. So now the question is, and similarly, then you may say that, okay, what about gamma ijk? Can it be used to probe flatness or curvedness? Okay. Answer is no. Again, polar coordinates, gammas are not equal to 0. But polar coordinate system can be transformed to Minkowski. So just by looking at Gij or by gamma ijk, I cannot say whether my system, my space-time is flat or not. So the question is, how do we do it? And for this, let us do the following simple physical experiment. Suppose I have a point A and a point B, and I have a vector here. And I transform this vector in this direction. I mean, parallelly transport this vector in this direction, and I transport this vector in this direction. Then I transport this vector in this direction, and I transport this vector in this direction. Then, after parallelly transporting on a loop in flat space, the final and initial vector coincide. Are you with me?
Yes.
Yes.
Okay. Alternatively, I can say that if I have a vector v and I take it to this point as a vector v, and then move it to this point and a vector v. Alternatively, I take it from here, this is a vector v, and I take it here, then both these vectors will be coinciding. In other words, from one point to another, when I transport a vector, the path of the vector does not affect whether the final vector is same or not. All right?
Yes.
Yes.
Okay. Now let me give you another example. Suppose I take a sphere and I take the North Pole and I have a vector over here. I parallelly transport the vector from here right up to here, and it is going down like this. Then I parallelly transport it by 90 degrees of longitude to here along the equator. And then I take it back over here and it will be like this. So what you see it, when I take this vector in a closed loop, in the case of the surface of a sphere, the vector changes its direction. Physically, this is achieved by taking a gyroscope in a closed loop. Okay. You understand what's happening?
Yes.
So you see one hint that if you move a vector in a closed loop, whether or not the vector is coming back to the original one or not, has an information about the flatness or curvedness of the space-time. Okay. And now we want to put it in a mathematical formulation. And for this, what we do is, I will do the mathematics and I'll tell you how it is related physically to this. Now I consider a vector AI. Okay. And let me get the covariant derivative of this vector. With respect to x G. And so I have A, I, semicolon J. And this quantity is actually a vector which I can write Bij because covariant derivative of vector is a vector. The covariant derivative of vector is a tensor. Now, this is where what Harish was asking some time back. If I do a second differentiation, what happens? That's what it comes here. Now, covariant derivative with respect to some other direction, xk, the kth direction, of Bij will be Bij semicolon k. All right. And so Bij semicolon k is equal to Ai semicolon j semicolon k. Harish, do you see this is the second derivative which is coming?
Yes, yes.
Okay. So this is this one. Now what I can do is, I can say that let me take the covariant derivative of Ai. Now with respect to first, I'll take with respect to xk. So here what has happened is, I went like this and like this. In the other one, went in the reverse direction and compared the vectors. I do exactly the same thing here. I first had with respect to xj and then xk. Now I'll do it with respect to xk first. And this will be Ai semicolon k will be equal to Bik. And covariant derivative of Ai of Bik with respect to xj will be equal to Bik semicolon j. And so Bik semicolon j is equal to Ai semicolon k semicolon j. And compare these two. Basically, the order of covariant derivative has been reversed. Now let me write. And now what I need to do, I want to compare these two. To compare these two, what I have had, I have gone through two different paths and I will find the difference of these tensors. Okay. And for this, first of all, I need to write it out. Explicitly. So I have Ai semicolon j is equal to Ai comma j minus gamma L Al Ij. All right. Very.
Yes, yes.
Okay. Okay. And I mean, and this is equal to Bij. And Bij semicolon k is equal to Bij comma k minus gamma L B K J L I minus gamma L B L I J K. All right. And now I will substitute it over here. So it means now this is equal to what? This is equal to Ai semicolon j comma k minus gamma L I k Al semicolon j comma k minus gamma L j k Ai semicolon L comma k. Now I'll expand this further. So this is A, I, comma J, comma K minus gamma. Okay, or so there's no confusion, I'll do it systematically one by one. Okay, so I have
Sesh,
huh?
in the second term, why are we differentiating with respect to like K ordinary derivative? There's just BLJ, right?
No, there is one mistake I have done. Just a minute. No, just 1 minute. Just a minute. B, I, J, L, L, K. What did I do? This is K. No, wait.
This is just the first term, right?
No, there's some mistake I have done here. This is this term. This is gamma IK.
I think the third term is not necessary here.
No, it's necessary. Just a minute. I've done some mistake here. Okay, wait. Okay, so let us see this. Yeah, Yajil, what were you asking about ordinary derivative?
I mean, the first term is fine, like bi comma j, because bij comma k is ai comma j comma k, and then the second and third terms you were differentiating with respect to k. I don't know why.
No, this K, no?
Yeah, but for the connection terms, those terms, you were also differentiating them with respect to k.
Yeah. So, okay. See, now look at it this way. I am now writing the left-hand side is, okay, so I have got Bij semicolon K. This is okay?
Yeah.
Now, this is okay. Now, I am not doing anything. I'm just saying that this quantity will be Bij is AI semicolon J.
Yeah.
This is being done partial derivative with respect to K. I mean, I'm just doing the del by del. I'm just substituting it mathematically for that expression.
Yeah. The next term, I mean,
This one?
the next term you have also differentiated it with respect to k, but I don't see any ordinary differentiation.
Oh, this is a stupidity I have done. This is wrong. That's the mistake. There's no differentiation there. Oh, yeah, I'm sorry. Yeah, you're right. Gamma IK AL semicolon J minus gamma LJK AI semicolon L. This is what it is. Isn't it?
Yes.
Yeah. Yes, this is what it is. And now what I'll do is, now I'll open up all the covariant derivatives. So this will be AI comma J minus gamma M AM JI. Is it okay? I just opened out AI covariant J.
Yeah.
Minus gamma, yeah, LIK AL comma J minus gamma M AM J L. Okay? And minus gamma LJK AI comma L minus gamma M AM LI. Now I have reduced everything to multiplication by gamma and ordinary derivatives. I got rid of all the covariant derivatives. Okay?
Yeah.
Now this is equal to ai comma j comma k minus gamma m I j comma k a m minus gamma m I j a m comma k. Okay. This one. Open it up. Minus gamma L I k a L comma j plus gamma L I k gamma m L j a m. So you see the interesting thing. You know, it has to do with the fact that, okay, I will come to it later. Yeah. Okay, so let's see, you looking at this, you have this first derivative of gamma. Now try to picture it. We know that gamma itself is like a first derivative of G mu nu, right? Gij. You know the expression I had given. You know, I had that expression, gamma ijk is equal to half Gia Gaj comma k plus Gak comma j minus this one. They're all first derivatives of G.
Yeah.
Right? Now
Yeah.
there is another derivative of gamma, which means it involves a second derivative of G. Okay? Do you get it?
Yeah.
Yes.
Now, we saw that G0 has to do with the gravitational potential. So, this involves a second derivative of gravitational potential,
Yeah.
which is basically the Poisson equation, del square phi. That's where the connection is coming.
Oh.
Okay?
Yes.
So, you already see that some, you know, signals of that Poisson equation already hitting you now. That there is a second derivative of phi coming in from somewhere in this. Okay. And now this minus gamma L jk ai comma L plus gamma L jk gamma m j il am. All right.
Yes.
Yeah.
Okay, fine. Now let us just try to collect terms. Okay, fine. So let me just write it out neatly so that, okay, so I have A I semicolon J semicolon K is equal to AI comma J comma K minus gamma M IJ comma K AM minus gamma M IJ AM comma K minus gamma L I K A L comma J plus gamma L I K gamma M L J A M minus gamma L J K A I comma L plus gamma L J K gamma M I L A M. Fine. Now what I do is I will write AI semicolon K semicolon J because that is what I need now. I want to do the differentiation among two paths.
Yes.
Right?
Yeah.
So I will reverse these two. So this will be equal to, basically I need to interchange J and K. I j comma k comma j minus gamma m I k comma j a m minus gamma m I k a m comma j minus gamma l I j a l comma k plus gamma l I j gamma m l k a m minus gamma l k j a I L plus gamma L K J gamma M I L A M. All right.
Yes.
Okay. And now what I do is I subtract these two because that is what I need to do. Okay. And now you see the magic. First of all, let us look at. Wait. Let us look at these terms. Let us look at these two terms. Since gamma is symmetric, gamma jk, gamma kj is the same. So these two will cancel out. Similarly, this is AIL. This is AIL, AIL is gamma jk, gamma kj. So these two will also cancel out. Okay. Then what I do is, let us consider these two terms. Let us consider gamma ij. No, I need. Okay, this I will not. Mk. Now you consider these two. Now, L is a dummy index. So I can make this L is a dummy index, and I can make this M and make this M. All right.
Yes.
And then I will I'll put it this way so that we know what we are cancelling. I cancel this and this. Similarly, I change this L to M, which makes it M, and then I will cancel this and this. All right.
Yes.
So what is it that I'm left with? I'm left with AI semicolon J semicolon K minus AI semicolon K semicolon J is equal to AI comma J comma K minus AI comma K comma J plus. Now there is an AM here, AM here, AM here, AM here. So I can write this as plus gamma M IK comma J minus gamma M IJ comma K plus gamma L IK gamma M LJ, which is here, minus gamma L IJ gamma M LK, this whole thing into AM. All right.
Yes.
Okay. Now, what is this object?
This ordinary derivative.
Yes. So what it will be equal to?
0.
It will be 0. Now, what you are basically saying is, if you have a flat spacetime, Minkowski spacetime particularly, these things will be 0 anyway because gammas will be 0. And so the covariant derivative will be ordinary derivative. And since in the ordinary derivative, order of derivative does not matter, the covariant derivative will vanish. And that is why when you take the vector from two different paths, they are equal and their difference becomes 0 in flat spacetime. Okay. Am I clear?
Yes.
Others?
Gammas need not necessarily be 0 in.
I'm talking about Minkowski, not just flat.
Okay.
Okay. But it will turn out, okay, I will just tell you something more. Okay. As far as gammas are concerned, there will be 0 if it is Minkowski.
Okay.
Okay. Now, so it means that AI comma semicolon J semicolon K minus AI semicolon K semicolon J is equal to an object which I write as R M I J K. I think that's what it is. Yeah. With into AM, where this is equal to this object. Okay. Is it all right?
Yes, yes.
Okay. But you see something interesting. Gammas are not tensors. But if you see this quantity is 0. This is a tensor, this is a tensor, so left-hand side is a tensor. This is a vector. So although gammas are not tensors, this combination is a tensor. Is that all right?
Yes.
Okay. And when you can see that if suppose you used a flat spacetime but used it in polar coordinates, gammas will not be 0, but this combination will be 0.
Yeah.
It has to be because I know that in Cartesian system, in a Minkowski system, this quantity is 0 because gammas are 0. Okay.
Yes.
Okay. So this quantity is okay. So gammas are 0. And so it means that this equation is valid in flat spacetime. Say it should be valid in all spacetimes because it's a tensor equation.
Yes.
Okay. So the interesting thing is the following, that this quantity is what encodes in it the curvedness of spacetime. So this is the central object for gravity. So when there is gravity, when there is no gravity, I can take a strange coordinate system, make Gij non-zero, gamma non-zero, and so on. But this quantity will be 0. This quantity will actually capture the fundamental nature of spacetime and without getting interfered with the what coordinate system I use. Okay.
Yes.
Okay. And another quantity which I define is R Nijk, which is equal to G N M R M I J K. Basically, I'm lowering the index, and this is called the Riemann. I mean, I'm not sure about the spellings and all. Christoffel tensor. Okay. And as I said, this contains the second derivative of Gij. So you know that this should contain something like the left-hand side of Poisson equation, del square phi. All right?
Yes.
Okay. Now, we will now build on this to build the theory of gravity. Okay? Because we are now got for the first time an object which can differentiate between curved geometry and flat geometry independent of what coordinate system I use. Okay. Now, what are the properties of this? Now, you can actually see that, I mean, okay, I'll give it to you as an exercise. So you will have R, N, I, J, K will be equal to minus R, I, N, J, K. That is, oh, what is low battery? Achha, this one. Okay. Okay. And okay, so that is, it is antisymmetric in the first two indices. Also, R, N, I, J, K recording failed to start. What is this? Recording failed to start. No, it's okay. Fine, whatever. Okay. Now, further, pointer, yeah. It is also antisymmetric in the second two indices. So JK is equal to minus R I, no, N I KJ. Another thing which you can see
I
is
don't think
that,
you're sharing the screen.
pardon?
I don't think you're sharing the screen. Or is it
Oh,
just me?
screen sharing has gone away, huh?
Yeah.
No.
No, we don't see the notepad. Like we just see the home screen. I mean, at least I see that.
Yeah, same with me.
Okay then.
Can you see the thing? No?
No, it's stuck in your home page. Like even your video is stuck there.
Yeah, now it's fine.
Not
Okay. Okay. So now it is, the another interesting thing is if I have R, N, I, J, K and just reverse these two pairs, then it is symmetric. Okay. And R, N, I, J, K plus R, N, K, I, J plus R, N, J, K, I is equal to 0. That is, if I keep the first one constant and cyclically rotate the other three, the sum is 0. Okay. So these are some important properties of this. And so now what let us see how many independent components of R which are there. Because since all these are related, all of them can't be independent. Because for example, if I know R1, 0, 2, 3, I automatically know R2, 3, 1, 0 because of this property. Similarly, if I know R1, 0, 2, 3, I know R0, 1, 2, 3 because of this property. So it means that all of these cannot be independent. So the question arises, how many independent components are there? So let us see this. Now, for a given Ni, I can have, suppose it is an n dimensions. I have an n dimensional spacetime. So for a given Ni, I can have NC2 combinations of jk. Why is NC2? Remember that it means that since it is antisymmetric in jk, when jk are equal, then it is 0. So it's already known. Okay, so that is why it will be half into n minus 1. Otherwise, it would have been half in, if this antisymmetry was not, there will be half into n plus 1.
Yes.
You get it?
Yeah.
Yes.
And so this is basically NC2. So there are NC2 combinations. That is, once I have selected, suppose j equal to 0, 1, 2, 3. K is 0, 1, 2, 3. If I have selected 0 for j, I can no more select k. I have only 3 left to select from. That's why it's NC2. Is it okay?
Yes.
Yes.
Okay. Similarly, for a given jk, there are NC2 combinations of ni. Because again, it's antisymmetric. But ni jk is symmetric. So number of independent components will be half into NC2 into NC2 plus 1. I mean, n into n plus 1 by half, that kind of a thing.
Yes.
Okay. So there are these many independent things. Now, here what I have used is only the fact, the first 3 facts. Now I have this extra condition. Now here what I am doing is, here the independent constraints will be out of n dimension, I can pick up any 4 because I have to fill 4 positions. If any 2 positions are equal, then there will be 0 and so on. Right?
Could you repeat that?
Suppose I choose n equal to 0, I equal to 0, j equal to 2, and k equal to 3. Suppose. Then what will this be? It will be R 0, 0, 2, 3 plus R 0, 3, ah, 0, 3, 0, 2 plus R 2, 3, 0, 2, 3, 0 equal to 0. Okay?
Yes.
Fine. Now, this is 0 because R0, 0, it is antisymmetric. All right?
Yeah.
This is antisymmetric, so I will make it 0, 3 and put a minus sign. Okay?
Yeah.
And since these are symmetric, obviously this is satisfied.
Yes.
So it means that when I have 2 things which are equal, everything is known. So I need to have 4 different values of n, I, j, and k out of the n different values in an n dimension. So the number of constraints are NC4. Okay? Is that all right? Because in n dimension, there are n coordinates. Out of that, I have to fill 4 positions.
Yeah.
So it's NC4, which means that out of these degrees of freedom, I have to subtract these many constraints. And this comes out to be 1 by 12 n squared into n square minus 1. So the total number of independent degrees of freedom, independent components of RIJKL is this thing. See, otherwise, how many components are there? There are n to the power 4 components are there, right?
Yes.
Is n power n into n into n into n, n power
Yes.
4, right? Yeah. now suppose, for example, take a 3-dimensional, suppose I have a 3-dimensional, or take a 2-dimensional thing. Okay, 2-dimensional surface. Here n equal to 2. There are 2 coordinates which define a 2-dimensional surface. So the number of, so 1 by 12 n square minus 1 is equal to 1. So just one parameter is the one which is required, and not 2 to the power 4.
Yes.
So if I get one non-zero value of Rijkl, I can immediately calculate all the other quantities just by the symmetry properties. And if n equal to 3, then it will be 1 by 12 into 9 into 8, which is 3 into 2, which is 6. And if n equal to 4, the usual space-time, then into 4, 16 into 15, which is equal to 4 into 5, which is equal to 20. There are 20 independent components of Rijkl in a 4-dimensional space-time. All right?
Yeah.
Okay. Now, I will define some more tensors, and the motivation is that they will be useful later. There is something called the Ricci tensor. The Ricci tensor is got by contracting this one. So I have Rijkl, and what I do is no, this is wrong what I have written. Rijkl Gij. No, ये गलत है. एक minute. This is wrong. I made a mistake. Yeah. So if I make this as I, then Rijil is equal to Gim or Gik okay, right. Just a minute. No, wait a minute. So I have Rijkl, and I will define Rjl as Rijil. Okay, I contract with respect to these two indices. All right?
Yeah.
Okay. And this is basically equal to G
Contravariant, right?
K no, wait a minute. Okay. So I have R I or M J K L, and this, okay, so this thing will be equal to, I have R M I, and I will call this also
R M
This will be the one.
Ah,
Okay. This is RJL. This is called the Ricci tensor. Now, the property of the Ricci tensor is it is symmetric. RJL is equal to RLJ. And then I can define one more quantity called the curvature scalar, which is equal to GJL RJL, which is equal to RJJ. Let me tell you significance of this. Suppose I take the surface of a sphere. Okay. It is covered by it's a curved geometry. And it's a two-dimensional geometry, just theta and phi, because the R is a given parameter, not a coordinate, right? Is that okay?
Sesh, can you, repeat the last two steps?
What I said was, if I take a sphere, then theta and phi are the coordinates on the surface of the sphere.
Okay.
R, radius of the sphere, is not a coordinate because it is given.
Ah.
Okay, it is
Theta,
not something which changes. There is no dr on that.
Okay.
Okay. Now, so I have for a sphere, I have I have theta and phi, and I have dl square is equal to r square d theta square plus r square sine square theta d phi square. There is no dr square because the sphere is given.
Yeah.
There is no radial, it only moves in 2 dimensions. Now, for this, the Gij is given by r square sine square theta 0, 0. All right.
Yes.
And now, and then, okay. And then from Gij, I can calculate gamma ijk. And from here, I can calculate Rijkl. From here, I can calculate RJL. And from here, I can calculate capital R. I mean, okay, I should we call it R bar. Radius of the sphere. All right. Just to distinguish from that curvature scalar.
Yes.
Okay. Now I can calculate R. It will turn out that R is proportional to 1 by R bar square. So it means that so when the sphere becomes a flat space, essentially the radius of the sphere becomes infinity and the curvature R becomes 0. Okay.
Yeah.
Okay.
So a completely contracted parameter is a measure of curvature.
No. Even the Rijkl has that. I can actually calculate Rijkl. There also it will have signature of this one. But this can be directly related to the radius. That Rijkl will have 0 as well as 1 by R square proportional to and minus 1 by R square proportional to different components. But the completely contracted thing will be proportional to 1 by radius square.
Okay, got it.
Okay. And yeah, now I can actually start generating an infinite number of things. For example, I can go ahead and define DIM is equal to Rijkl RMJKL. This is also a scalar. This is also a two-dimensional tensor. And there are so many. It turns out that Rijkl, Rij, and R are the ones which are useful tensors in GR. And I will come to this issue later. What happens when you kindly find these higher order tensors? Okay. So once you have that, then we are ready to start launching into the left-hand side of Einstein's equation, which is geometric. So as I have been telling, GR relates geometry to matter through a tensor equation. So I need geometric. What is happening? On screen broadcast, the problem, is it? Are you able to see the screen?
Yes.
No, but it's stuck for me. Like,
Oh, yeah.
I think it's the charging phase. Like, whenever you charge your device.
No. There's a problem with the internet. Zoom is back. Oh, Zoom had gone off. Okay, I will just do this. Just a minute. Just hold on. Can you see the screen?
Yes.
Yeah.
Okay, so this was the last portion which I had, so I'll just do it from the laptop itself. So I have GR is related to this one, and so the required structure is this quantity. The geometric tensor should be equal to matter tensor. And the geometric theory requires that we have to choose a left-hand side and right-hand side appropriately, and this is where enter Einstein. Now Einstein was at work. First of all, there is already from things in fluid dynamics, we knew what kind of a matter tensor should be there. That I will do an aside, and then I will discuss about energy momentum tensor. Then Einstein started substituting one by one various geometric tensors like Rij, Kl, Rij, R, and so on, and various combination, giving some physical reason as to what should be the left-hand side to satisfy some basic requirements of my theory. And that is how he arrived at the Einstein's equation, which I will do next time. Is that okay?
Yes. Yes.
Yes,
Yeah.
yes.
Good. Yep. Anything? Okay.
Well, let's just.
Okay.
Thank you. Thank you.
Chalo.
Good night. Bye.
Bye
Bye.
bye. Bye bye bye.